Welcome back. Today we're doing another simple science summary of further studies physics, and we're diving into something really foundational: how charged particles behave in electric and magnetic fields.
Yeah, it sounds abstract, maybe, but it's actually the key to understanding so much. From tiny particle interactions to huge technologies like particle accelerators.
Exactly. We're talking about exploring the universe's basic ingredients, even medical breakthroughs. It's pretty crucial stuff.
Absolutely. So, our plan today is to unpack the core ideas and, importantly, show you how they're used in the real world, high-tech stuff, including things happening right here in South Africa. This isn't just textbook theory, it's active science.
Great. Okay, let's start with electric fields. We know they surround charges, we draw field lines, but remind us, what's the absolute rule for the direction of those lines?
Well, the definition really, is the direction of the force on a tiny positive test charge. So lines point away from positive charges and they point towards negative ones.
Right. So a positive charge gets pushed with the field, and a negative charge gets pushed against it.
Precisely. It's like knowing which way the current flows in a river for charged particles.
And if we have a uniform field, like between two charged parallel plates, how do we figure out how strong that field is?
Okay. For a uniform field, the strength is just the potential difference, the voltage between the plates, divided by the distance separating them. Simple relationship, V over D.
So more voltage means stronger field, bigger gap means weaker field. Makes sense.
Exactly. And it means we can tune the field strength very precisely.
Okay, so field strength calculated. If we then put a charged particle in that field, how do we know the force it feels?
Well, the force is simply the particle's charge multiplied by the electric field strength. That's it. F equals Q times E.
And the direction depends on the charge sign, like you said.
Yep, positive goes with the field, negative goes opposite.
This actually leads to a classic experiment, doesn't it? Millikan's oil drop.
Oh, absolutely. A brilliant piece of work. Milikan used a carefully controlled electric field to suspend tiny charged oil droplets, balancing the electric force upwards against gravity pulling downwards.
So he was essentially weighing the charge.
In a way, yes. By finding the exact field needed to balance a drop, he could calculate the charge on it. And he found the charges always came in multiples of a basic unit.
The charge of a single electron.
Exactly. He measured the fundamental unit of charge, proved it was quantized. Just fundamentally important work based on these simple force principles.
Amazing. Okay, that covers electric fields. Now, let's switch gears to magnetic fields. How are they similar, but crucially, how are they different?
Okay, similarity first. We also use field lines. They show direction out of north into south, and strength, closer lines mean a stronger field.
Right, but the difference?
The big difference is how they're made and how they act. Magnetic fields are only produced by moving charges like currents in a wire or electrons orbiting atoms. And, this is key, a magnetic field exerts no force on a stationary charge.
None at all.
Zero force. The charge has to be moving relative to the field to feel anything. That trips a lot of people up.
Okay, that's a huge distinction. So for a moving charge, what determines the force, the Lorentz force, right? And how do we find its direction?
Right, the Lorentz force due to the magnetic field. Its size depends on the charge, the velocity of the particle, the magnetic field strength, and, importantly, the angle between the velocity and the field. Maximum force when they're perpendicular.
And the direction.
Yeah.
Not as simple as with electric fields.
No, it's always perpendicular to both the velocity and the magnetic field. We use the right-hand rule to figure it out.
Ah, yes, the right-hand rule. Remind us how that works.
Sure. For a positive charge, point your thumb along the velocity vector, your fingers along the magnetic field vector, and the force pushes out from your palm.
Okay, thumb for velocity, fingers for field, palm for force.
Yep. And if the charge is negative, the force is in the exact opposite direction to what the rule gives you. You just flip it 180 degrees. It's essential for figuring out where particles will go.
Got it.
Yeah.
So now we know how electric and magnetic fields push charges around. How do we actually use this? What happens when particles enter these fields?
Well, in a uniform electric field, like we said, they get deflected straight towards the oppositely charged plate. Positives go one way, negatives the other, like rolling a ball down a slope. Neutral particles, they just fly straight through, unaffected.
Okay, straightforward deflection. But magnetic fields.
Magnetic fields are different. Because the force is always perpendicular to the velocity, it doesn't speed the particle up and slow it down, it just changes its direction continuously, leading to circular or spiral paths. The magnetic force acts as the centripetal force, constantly turning the particle. Think of those beautiful tracks in old bubble chamber photos from CERN. Those curves are charged particles bending in a magnetic field.
That's really cool. Okay, here's where it gets even more clever, I think, combining them. The velocity selector. How does that work?
It's a really neat trick. You set up an electric field and a magnetic field that are perpendicular to each other, and also perpendicular to the direction the particles are initially moving.
Okay, E, B, and velocity all at right angles.
Exactly. Now, the electric field pushes the particle one way, say, upwards. The magnetic field pushes it the other way, downwards.
Ah, tug of war.
Precisely. And the magnetic force depends on velocity, remember. So there will be one specific velocity where the magnetic force perfectly balances the electric force.
So only particles with that exact speed feel no net force.
Exactly. They just sail straight through, undeflected. Faster particles get bent one way by the stronger magnetic force. Slower particles get bent the other way by the relatively stronger electric force.
And the clever part?
The really clever part is that the selected velocity just depends on the ratio of the electric field strength to the magnetic field strength, V, E split. It doesn't depend on the particle's charge or its mass.
Wow. So you can pick out particles of a specific speed regardless of what they are. That seems incredibly useful.
It is. It's often the first stage in devices like mass spectrometers. You need a beam where everything's moving at the same known speed.
Okay, let's talk about that. Mass spectrometers. We've got our beam, all particles at the same speed thanks to the velocity selector. How do we then figure out their mass, especially for tiny things like isotopes?
Right. So after the velocity selector, you send this uniform speed beam into another region, this time with only a uniform magnetic field. Again, perpendicular to their velocity.
Okay, velocity selector done, now just a magnetic field.
Yep. And as we said, a magnetic field makes moving charges go in circles. The magnetic force provides the centripetal force.
And the radius of that circle.
The radius depends on the particle's momentum, mass times velocity, and its charge, and the magnetic field strength. Since we know the velocity from the selector and the field strength, and we can measure the radius of the path they take.
We can calculate the mass-to-charge ratio.
Exactly. Heavier particles or particles with less charge will have larger radii. Lighter particles or more highly charged ones will curve more tightly.
So you physically separate particles based on their mass-to-charge ratio.
Precisely. You ionize your sample, accelerate the ions, select a single velocity, then bend them in the magnetic field. They hit a detector at different positions depending on their radius, which tells you what isotopes or molecules were in the original sample.
That's how they separate isotopes like uranium-235 from U-238.
That's one critical application, yes. Essential for nuclear fuel.
Yep.
But it's used everywhere: chemistry, biology, geology, forensics. It's a workhorse instrument.
Okay, from balancing oil drops to sorting isotopes.
Yeah.
Now, the really big stuff, particle accelerators. Why build these massive city-sized machines? What's the point of such high energies?
That's the fundamental question, isn't it? Why so much energy? It comes down to Einstein. E.m.c. part and fork thrust, energy can be converted into mass.
Ah, so you smash particles together with huge energy.
And hope that energy transforms into the mass of new, perhaps undiscovered, heavier particles. Particles that might have existed only in the very early universe, or that our theories predict but we haven't seen yet.
So it's about creating matter from energy to test fundamental physics.
Exactly. Plus, magnetic fields are crucial not just for guiding the beams, but also for squeezing them, focusing them down to tiny points to increase the chance of collisions, overcoming the fact that all the particles in the beam are trying to repel each other.
Let's look at the types. First up, the linear accelerator, the Linac. Sounds straightforward.
It is, in concept. You accelerate particles in a straight line down a long tube. Inside the tube are sections, or cells, with gaps between them. An oscillating electric field is applied across these gaps.
So the particles get a kick of energy each time they cross a gap.
Precisely. The timing is critical. The field has to be pointing the right way to accelerate them just as they arrive at the gap. And because they get faster after each kick,
the cells have to get longer, further down the tube, so the particles spend the same amount of time in each cell, even though they're traveling faster.
You got it. Successive cells get longer and longer. Linacs are versatile, used for medical treatments, industrial applications, and often as the first stage, the injector, for bigger circular accelerators.
Okay, so Linacs are straight. What about cyclotrons? They bend the path.
Right. A cyclotron uses a clever combination. It has a large constant magnetic field that covers the whole area. This field makes the particles go in circles.
Okay, constant magnetic field for bending. How do they accelerate?
They use two hollow D-shaped electrodes called Ds. An alternating voltage is applied between the Ds. Particles start in the center, get accelerated across the gap between the Ds, then the magnetic field bends them around in a semicircle inside one D.
And they cross the gap again?
Exactly, but the voltage has now flipped, so they get accelerated again. They gain energy, speed up, and because they're faster, the magnetic field bends them in a slightly larger semicircle.
So they spiral outwards.
They spiral outwards, getting faster and faster with each turn until they reach the edge and are extracted. Cyclotrons were the first really high-energy machines and are still vital, especially for making medical radioisotopes, like the fluorine-18 used in PET scans.
PET scans, right. Okay, Linac, cyclotron. Now the biggest ones, synchrotrons, like the LHC at CERN. How are they different?
Synchrotrons also use a circular path, but it's a fixed path, a ring. They don't spiral outwards. They use magnets placed strategically around the ring just to bend the beam and keep it focused, and separate accelerating cavities using radio frequency fields like Linac gaps to boost the energy on each lap.
So the path radius stays the same, but the particle's getting faster, more energetic.
Exactly. Which means the magnetic field in the bending magnets can't be constant like in a cyclotron. As the particles gain energy, you have to increase the strength of the magnetic field in sync with the energy increase to keep them bent onto that same fixed path.
Ah, synchronized magnetic field increase, hence synchrotron.
Precisely. And they need an injector. They can't start particles from rest. They need a Linac or a smaller synchrotron to give the particles their initial kick. This design lets them reach much higher energies than cyclotrons, keeping the ring size manageable. That's why the LHC is a synchrotron.
And these synchrotrons produce something else, amazing synchrotron radiation.
Oh yeah, it's actually a byproduct, but an incredibly useful one. When you take charged particles, especially light ones like electrons, traveling near the speed of light and force them to change direction using strong magnetic fields.
Like the bending magnets in a synchrotron ring.
Exactly. They radiate energy away, they emit electromagnetic radiation light, but because they're moving so fast, this light is incredibly intense, highly focused, and covers a huge range of wavelengths, from infrared right up to very hard X-rays.
Brighter than anything else.
Orders and orders of magnitude brighter than conventional X-ray tubes. And you can tune the wavelength you want. It's like having a super powerful, tunable microscope.
What do scientists use it for?
All sorts. Determining the precise atomic structure of materials, analyzing complex proteins to design drugs, looking inside operating engines, examining ancient artifacts. It's revolutionized countless fields. Many Nobel Prizes have come from work using synchrotron light.
Incredible. Now, talking big science, we have to mention CERN and the LHC. It's just mind-boggling in scale.
It really is. The Large Hadron Collider near Geneva. Almost 27 kilometers around. It's the largest machine ever built by humans. It takes protons through a whole chain of smaller accelerators, Linacs, booster synchrotrons, before they even get injected into the main LHC ring.
And the conditions inside
Are extreme. Colder than outer space, just 1.9 Kelvin for the superconducting magnets to work. A vacuum more empty than interplanetary space so the beams don't hit stray air molecules. It smashes protons together at energies, simulating the conditions just moments after the Big Bang. It's where the Higgs boson was discovered, a true testament to international collaboration.
It's amazing. But, we don't actually have to look all the way to Switzerland to see this kind of advanced physics making a difference, do we?
No, absolutely not. We have a world-class facility right here in South Africa. iThemba Lab ES.
Tell us about iThemba Labius.
It's the Laboratory for Accelerator-Based Sciences, part of the National Research Foundation. It's Africa's largest facility for this kind of research, mainly based near Cape Town, with a smaller site in Gauteng, too. They operate several particle accelerators, including a big, sophisticated, separated sector cyclotron.
So fundamental research like CERN.
They do fundamental nuclear physics research, yes, contributing to our global understanding, but they also have a huge focus on applications. They are one of the world's major producers of medical radioisotopes.
The ones used in scans like fluorine-18.
Exactly, fluorine-18 for PET scans and others. They supply hospitals across South Africa and internationally. It's a direct link from accelerator physics to healthcare. And even more directly, they have a dedicated medical facility that uses beams of protons and neutrons from their accelerators for cancer therapy.
Wow, direct cancer treatment using particle beams.
Yes, proton and neutron therapy. It's a highly specialized form of radiotherapy. So iThemba is a perfect example of how this deep physics knowledge translates into tangible benefits for society, right here.
It really brings it all together. So looking back, from the simple force on one charge, FQE, and the curling force from magnetic fields, to building these enormous complex machines like synchrotrons and facilities like iThemba LABs, it's clear this isn't just equations.
Not at all. It's the engine driving exploration at the smallest scales, finding out what we're made of, how the universe works, and at the same time, it's driving innovation in medicine, material science, and so much more. It's truly at the cutting edge.
It really is inspiring. So as you continue your further studies physics journey, maybe think about this. Where does this go next? What could the next generation of accelerators reveal about the universe? Or what completely new applications might pop up from mastering these forces even better? The possibilities seem, well, almost limitless. Thanks for joining us for this simple science summary of FS Physics. Keep digging deeper, keep asking questions, and keep learning.